So thanks a lot, John, for this opportunity, and I'm really thrilled to present some of the work, and mainly that work has been done within our group by Ali during his PhD, with contribution by a number of other members of the group. So what we would like to talk is really how we can characterize the fracture complexity and the type of fractures in the laminated Montney Formation. That has been done through laboratory true-triaxial hydraulic fracturing test, and that is really, I think, the key experimental capability that we have here at U of T that we took advantage for in this particular study. So the Montney Formation is really the largest unconventional hydrocarbon play in Canada, and is to date really there's not really publicly or published fully comprehensive hydromechanical characterization under the real in situ stress state condition of the Montney shale, and the Montney Formation is a siltstone. So, and when you look a little bit more at literature, it's very rare to find any characterization under the real reservoir conditions of unconventional play in publishing literature. So what we have specifically to the Montney is a transition from a thrust fault regime very close to the mountain range to a strike slip regime in the location that we were studying, and that is the type of regime that we used in our test. So just as a brief sort of a part of the introduction, what I would like is to point the fact that the Montney shale, as the Vaca Muerta, the Eagle Ford, the Marcellus shale, because of the way they've been deposited, they really they have a bedding planes that are really everywhere within the formation that have been completed, and I think this play a very big part of the story in how this type of material respond during stimulations. Now, going back to the Montney, so as I was saying, is that the area where we were interested is really in a strike slip regime. At least that was what was published and found and calculated through the Earth model. And specifically to our area of study, what we back calculated or we imposed was the maximum horizontal stress sigma 1 of 63 MPAs and a minimum horizontal of 53, and the overburden stress, the vertical, about 49. So basically the overburden and the minimum principal stress are quite close together. And that is actually an important observation that will play in a role in our analysis. So one of the motivation for this study is that we wanted really to reproduce what an horizontal completion was doing to the rock. So how was the fracture was propagating under such a stress regime. And so what we were imposing was we're planning to have a cube to drill a horizontal well, the direction of sigma 3, and then complete that well to simulate a single stage open hole completion. And what we are expecting is, as literature and the models would tell us, is that a nice bi-wing type of fracture that would open against sigma 3. What our experiments consistently showed that that was not happening, and despite everything, we were open against sigma 2. Our fraction that was very consistent within all our experimental test campaign, and and then So what we were using, we had access to two different type of Montney Formation. One was outcrop in the area of Canmore, just north of Calgary in Alberta, and the other we had the fortune to have access to a full core that was recovered at depth in the Blueberry area of the Montney Formation. So we had these two, both the outcrop and at depth formation. So, and the other thing we had was the access to the experimental capabilities that is available at University of Toronto. So a true triaxial cell that is able to bring a cube that can be produced from our rock, both at depth, it's the core, and from surface or outcrop in a cube that would be brought to the stress conditions that are typical of the at the depth where general completion would take. And I will stop here and I will pass the stage to Ali.
Hello. So here we just explain a bit about the true-triaxial vessel that we have. So it is capable of applying independent stresses on each side. So you can apply on all 6 actuators. So we independently apply sigma 1, 2, and 3. It has LVDTs or 3 LVDTs across every face, fitted with P1, S1, and S2 sensors, and it also has 6 AE sensors on each face. Now, we will not discuss much about the AE in this presentation, but it is fair to say that all the events that occurred were very silent. Now, how do we achieve this is basically by creating a mini well packer that goes into the cube through an injection hole, and that goes inside the polyaxial cell, and that cell goes into the polyaxial machine. What we're trying to mimic here is an open hole scenario where we have 5 millimeters somewhere in the center of the cube, where we try to pressurize the hole and break the rock. Just to give you more context, again, this is how the platen looks like on the left side with the packer installed at the end. That goes inside the hole, which you see an image of a post-test. And again, inside the polyaxial frame. And on the top right, you can see the monitoring station where you are able to control all the parameters during the test. What we are expecting to see is something typical of a fracture curve where you see fracture initiation, propagation, and some kind of closure pressure during the pump. So let's bring this into context of first, the outcrop sample. So here we have a sample. As you can see, sigma 3 is 37.7, sigma 2 is 42.2, and sigma 1 is 54.6, which is under strike slip. What we see in red are the bedding planes, and what we see in green is the fracture. We'll talk about that later. But we injected the fluid at 7 milliliters per minute, and this is what we got. The fluid in this test was water. And as we can see, this is a typical pressure time curve that you would see. We also indicated sigma 1 and 2 and 3 for reference in this case. Now let's break down this curve. So what we have is the cavity filling, the open hole pressurization, pressure ramp up until you reach a maximum pressure, which is considered your breakdown. And then after that, you have what we call an unstable pressure relief and fracture propagation stage. And at some point towards the end, you reach a steady state pressure. Now, what we want to highlight here is that the steady state pressure is equal to sigma 2. This is key as we move on in the presentation. However, let's now take a closer look at certain locations within this pressure time curve. So first, I'll draw your attention here, and I'll spend some time talking about the inset or the small curves that appeared here, because this will appear in all the next slides. So on the top, what we have is schematic of the fracture. So here we have this fracture schematic. We will show how we reach this stage later on. And then we have the pressure time curve at this section. So you see the ramp up, breakdown, and then followed by pressure recovery. Here we see the dotted line is the averaged response of the LVDT, and the solid line is the actual raw data unsmoothened. So we see it in the X direction and the Y direction. So we will see this format in all the remaining slides. However, in this case, we want to highlight this. what we see here is an actual response of opening in or against the sigma 2 direction. So the cube basically opened against sigma 2. We look at another part of the curve, a similar analogy with the similar type of inset that you see. The dashed line is again the average response. But when you look at the raw data explicitly, you see a jump in your LVDT response. So these two jumps are basically a sudden opening or a sudden movement against the sigma 2 direction, which as we can see from these fracture, again, we will see how we got these later on. But as we can see that there is actually a fracture that's opening in or against sigma 2. If we look at other parts of the curve, we will notice that the pressure recovery, in these both cases or in these both instances, we are saying that this is a tensile fracture or this is a tensile opening or an opening. And the pressure recovery in this case is 1.16 MPa per second and 1.4 MPa per second, which are similarly close. So we can say that if we have a tensile fracture or a tensile signature or an opening signature, you are expecting to see a sudden movement in the LVDT and a pressure recovery that's in the range between 1 to 1.5 MPa per second. So these two will classify, or we will use to classify as a tensile failure or an opening. Now let's look at other parts of the curve. For example, we look here. What we see here is that there is no sudden response in the LVDT at all. It seems like it's just moving or shearing or sliding. And this is confirmed from our analysis of the fractures, which we will touch on in the next slide. What we also see is the pressure recovery. So after the fracture, after the drop in pressure, the recovery is way less than 1 MPa. It's around 0.4 MPa per second. So we can say that this is the signature of a slip event. Now, as I said, we will look into these fractures a bit more in details. So with the contribution of the students in our group, Ms. Mei Li and Ms. Phyllis and Sir Earl, we were able to take the cube out of the after testing and then inject it with epoxy and fluorescent epoxy to be more specific. And then through serious sectioning, they were able to grind down the cube into layers of 50 microns and then map the fractures and then see where the fractures are going through the cube. And through reconstruction, you were able to capture the fracture network. So here we see a primary fracture and we see the secondary fracture here at the bottom. So it doesn't just tell us this, it tells us that you have a primary fracture, you see shear-like features here where the initial of fractures, you see the Horst and Graben features where the fracture or the injection fluid is slowly trying to infiltrate into the impurities or the imperfections inside the rock. So we can capture much more in detail the specifics of every single fracture within that specific sample. So this was the outcrop sample. So it was a solid sample from an outcrop. Now we were lucky enough to have whole core samples. These are from a depth of approximately 2 kilometers below ground. And before testing, we CT scanned this core, and we know that before we test, there's a pre-existing fractures that runs almost along the core axis. So in this specific presentation, we'll be talking explicitly about sample B2. So with sample B2, we got 2 cubes. In the first cube, we injected with low viscosity fluid, which is the slick water. And this is the stress regime that we applied. And again, this is the pressure time curve. Now, when we look closely at the pressure time curve, we start seeing similar responses to shear or to opening. To shear or slipping. This is seen here. It is seen here, where you have no abrupt movement, but rather just slow movement or slow slipping. And the same here. So what we can deduce from this is that the events that occurred here were all slipping of shear or slip nature. What we also notice is that the shut-in pressure is lower than sigma 3. Now let's look at the next sample in B2, which is, in this case, we injected high viscosity fluid, Tide pods to be more specific. And in this case, we have the pressure time curve. What I want to highlight is these drops or these anomalies are just because of the way we were pumping. We could have eliminated this. However, during the experiment, this occurred. So this is just an anomaly of the pressuring system that we were using. Again, we start looking at every event in detail, and here we start seeing things similar to a tensile fracture, where you see the sudden drop in your LVDT or the sudden movement in your LVDT, indicating an opening. And in this case, the opening is in the sigma 2 direction. And then a similar event here where we see the opening against sigma 2. Something that is different between this sample and the outcrop is the lag, the time it takes between the initiation and the movement. In this case, it is around 5 seconds. In the case when using low viscosity fluid, it is much less. I think it is 1 or 2 seconds. So in this case, in this cube with the high viscosity, we've seen that we have opening fractures. Now let's try to put all these results in the context of their shut-in pressure. So what we see here is the 3 samples that we tested: outcrop 1, B2O1, which is the low viscosity fluid, and B2O2, which is the high viscosity fluid. What we see with the shut-in pressure is when we have a planar fracture, the amount of pressure required to keep the fracture open in outcrop 01 is exactly sigma 2. So that means we've just opened against sigma 2 one clean fracture. When the shut-in pressure is more or less than one of the principal stresses, we can assume that that is a proxy to the complexity of the fracture network that has been generated during the test. So this is in terms of shut-in pressure. Now, when we look into this in terms of the breakdown pressure, so we've highlighted the breakdown pressure as triangles, and then using, or we have proposed a new approach to how to calculate or approximate the breakdown pressure. And over here, we see that the pressure required to open against sigma 2 is actually closer to the breakdown pressure. So the assumptions or the method that we're putting forward is very close to the actual breakdown pressure that is occurring within the system or within the sample. And it also proves the fact that they're opening against sigma 2 and not sigma 3. So to conclude, the breakdown model that we propose captures both the in-situ stress and the rock strength anisotropy. And we also were able to find unique breakdown signatures in terms of tensile, where there's a abrupt strain response. And if you're using the high viscosity fluid, you have a lag between your initiation and your breakdown. And there is very little response or very subtle response when using shear. And the shut-in pressure shouldn't be just tied to the principal stress, but it can give you much more information than we actually think it does. And then high viscosity fluid will always lead to a hydraulic fracture with limited interaction between the existing weakness planes and discontinuities. So these were the findings from our study, and then I will pass it on to Professor Grasselli.
So what we found very interesting of this work is, first of all, that the anisotropy in strength of the material, and specifically on the tensile strength, is a key aspect. And most of the study done so far, they do not really account for this difference. So in other words, opening a bedding plane is much easier than opening the rock perpendicular to it. So that is a plane of weakness that should be accounted when you look at the at how to model such fracture propagation. The second part is that the fluid, and this really confirms what the literature and other studies have shown, is that as a big importance in how the fracture will propagate into the rock, and much higher viscosity will sort of probably in a bad way, we can say, is sort of homogenize, make more isotropic your rock, because the fluid has more difficulties in penetrating the pre-existing fracture discontinuities of bedding planes. So, and this actually I think is important, and is something that companies like, I think, Shearfrac are taking advantage when they try to engineer how the fracture is, how to control the fracture during completions. Now, when we look a little bit more in details at the cubes that we completed, in particular, this is the fracture network that has been mapped from the cube. What we can see is that from the cube recovered from the core at depth. So what we can see is that we see basically three families of fractures that were mapped. One is this vertical fracture that is pre-existing natural fracture we knew was there. Others are basically the bedding planes. There's a lot of planes that open that are really oriented along the bedding plane orientation. And then you have few small fractures that sort of are we call bi-winged or hydraulic fracture, classical hydraulic fracture failure that are really connecting the some of these bedding planes and the natural fracture. So basically, we have three different families, but by really mapping digitally this fracture network, what we've been doing and we've been able to do is really to start quantifying what is the volumes and percentage of these fractures. And to our surprise, is that almost over 60% of the fractures that were connected and lubricated or completed during our experiments, so basically of our stimulated rock volume, are made of bedding planes. About 28% was the natural fracture that we knew was there, and only 11, so that were fracture that we did not fall in any either of those two previous classes. So we called as bi-wing fractures. So, but these are really, this 11% is what normally is modeled and is aimed for. So we, as an industry, when if we assume that fracture will propagate as a bi-wing, we're actually missing basically 90% of the volume that really might be created because of the rock, of the presence of the bedding planes and natural fractures. And what I would really say is that the bedding planes have twice more impact than a natural fracture in the total final volumes. The other thing is really important that we notice is, at least for our test, when we look at the aperture distribution of these three fractions, we look at these varying plots, we see that both the bedding planes and the natural fractions have larger apertures than the bi-wing fractures that were created. So now, in another way, they are larger, so they conduct much more fluid. So from a production point of view, they are really becoming the key aspect, not just because they have much larger volume, but also because they have a larger aperture. And just using a simplistic cubic law, that tells you that these families, the bedding planes, natural fracture, might have a couple of order, three order of magnitude more importance than the bi-wing fractures into when you calculate your flow. Now, so that was on a cube of 8 centimeters, so not very big. So it's basically a 3 inches cube. But one of the big thing that we are working is really try to see how we can relate or link this to much larger fractures or much larger field operations. Now, let's completely change and let's look at what we can actually look and gain from other way to see at our completion. And for example, recently we are more and more interested in INSAR data. INSAR data is a really nice way to monitor uplift and movement of the surface of the Earth from satellite. And what we have been shown recently by Dave Eaton, Sergei Samsonov et al. It's that INSAR can pick clear signature of uplift associated with the completion. And those completions, so injections, those completion might be actually associated with large magnitude events, like those that have been happened in November 2022, 4.7, 4.5 events in close to north of Fort St. John's in the mountains. And again, when you look at the signal from INSAR, what you can see is that you can definitely see a clear vertical displacement, vertical component that is very similar to what we saw through LVDTs in our experiments. So what we were trying to start thinking is that what we see in our small cube through LVDTs might be able to be monitored through INSARs in the field. That's interesting. So at this point, this work that is currently undergoing is as we are trying to use a much larger cube, the 70 centimeters cube. So it's basically more than 2 feet high cube that will be completed. It's currently going to be completed. And what we're going to look is the effect of a larger volume on the propagation of our hydraulic fracturings. And we're going to try to get as many information as we can out of these larger blocks, just to answer the question if the small cube we had operated with up to now reproduces just a near well phenomena, or can be really used as proxy for what is happening at larger volume in the reservoir. So this will give us some hints on how much we can, or how we can upscale our results. So, and I hope we will have the possibility to present this work shortly, early next year, similar in this venue. But what we have done, and I'm very excited to share with you today, is we've been running a lot of numerical models using finite element, discrete element methodology. And these models will reproduce what will be the completion in one of these large size 70 centimeters cubes that have been characterized by several main planes that are introduced into the block horizontally. So now these planes are a proxy for those regional contacts, the tops of the different formations that are regional events that are really connected through your entire region. And what we did using the finite element, discrete element with Irazu is start completing at the center of our block and see how the fracture was going to propagate and interact with these features. And what we could see is that the fracture was really propagating. In this case, sorry, I forgot. Sigma 1 is actually your vertical stress, and you have two equivalent sigma 2 and sigma 3 horizontal. So what we saw is that the fracture will start propagating in a sort of bi-wing way until it got a little bit preferential opening along the direction of our bedding planes that were imposed horizontal. But when it reached one of those regional planes of weaknesses, very quickly opened and with no effort split the cube in two. Now, the other thing I would like to point you is this uplift that was calculated at the surface of our sample, and this is very similar, if you wish, to the expression that INSAR sees during completion that leads to eventually large seismic induced event. And what we can see, if we think that the model is capturing what the reality is, we can see that the effect of presence of bedding planes will create preferential opening along those bedding planes, and that is very similar to what we observe in our small cube. But when that fracture hit one of those regional features, it opens very quickly and can reach and lubricate transfers even kilometers away, that could lead to major events, and that would be induced by such lubrication. And I'm very keen to see if to further see the models run, and to couple that to our main large megalith experiments, and see if in reality we can tie everything together from our 8 centimeters cube to the 70 centimeters cube to the regional scale on the Montney. Now, with this, I think we will stop here our presentation, and just a little bit of advertisement. If ever you are intrigued about these results, join us at the GUSOF conference. It's just in a month, and we're going to present a little bit more recent results of the megalith cube, and we'll be having the chance to discuss in person. And thanks again to all our sponsors that have been supporting us during this long journey, that especially Ali, long journey to his PhD. So at this point, I thank you for listening, and we are ready for some questions.
Thank you both, Giovanni and Ali. Very, very informative and maybe a little bit controversial. And we do have some questions that reflect people's interest. And so Wenfeng Li wanted to know the measurements of tensile and shear strength of the bedding planes, and how those might differentiate from matrix strengths.
Yep. So we actually did do indirect tensile strength tests on different angles within the sample before we tested, and they are on the schematics of the cube. I think it was 14 MPa and 8 MPa, if I'm not mistaken. So over here, for example, it's 14 MPa and 3 MPa. So there is a huge anisotropy when you look at the tensile strength of what you consider as a matrix and what you consider as a bedding plane failure.
Okay.
So just to add, part of our work that's not been presented here is really to characterize the anisotropy and strength of the material. So what we are doing is really testing the same core, same horizon at a different angle, and we test both under triaxial, uniaxial, and also tensile stress state, and that is the way we characterize the anisotropy, and we use that in actually the model that was presented in our last slide.
Okay, thank you. And Ed Siebert would like to know, did you compute where your lab tests are located in the parametric space, our standard parametric space of viscosity versus toughness versus leak-off? And how does that compare with a typical field scale Montney behavior?
The short answer is no, we did not compute that.
Okay.
So we will.
Do you want to speculate?
Well, what I can say is that the only thing I can really say is that the fluid we use is a slick water that was recovered from a recirculation pit on site. So it's exactly the type of fluid that was used for that location. For the high viscosity, we got the highest viscosity fluid that we could inject, because we wanted to go really on the extreme. I don't think has been ever injected so viscous fluid at that on those operations. And my knowledge, and if I recall better, is that all the completion that we have been well, we had data shared with companies were using just leak water.
Okay. Okay, thanks. And Andrew Madyarov, Andrew's question is, do you have any indication of how fast the fracture reached the outer sides of the block? With the slick water injection, it may be milliseconds within the first breakdown peak.
Yep, that is correct.
Yes.
We do have track of how much time it took.
Yes. So that was from an experimental point of view, one of the challenge, because when the fraction really start propagating, was reaching the end of the block very quickly, and that was basically when we were stopping the completion. Then we tried to look a little bit better what was happening if we were starting injection again, and how the tube was behaving, but knowing that we were already at atmospheric pressure at the end of basically your injection path.
And so Shan Wu has a similar question, and maybe you could elaborate a little bit more. I mean, how did the loss of fluid impact the experimental results?
Do you mean loss of fluid or loss of pressure? There is no real loss of fluid.
So only your fracture went to the edge, your fluid did not make it to the edge?
So the fluid made it to the edge, and then we collect the water on the outside.
I see. Okay.
So basically what we created was a fluid flow with atmospheric pressure on one side and injection on the inlet. So now that is to answer these questions. I don't think we are, well, we can speculate, but the megalith and mega block experiment is really there to try to make sure that we can a little bit contain the more limit the extension of the fracture, and really have a longer time that would be I would say valid and reasonable for the analysis. Right now, for sure, the beginning is valid when you get quite quickly the fluid with the fracture at the boundary. We know that the boundary conditions are not representing anymore what the reality is, and that is why the larger larger cube will help us to get more insight in the fluid and pressure response. Despite that, what we were really focusing in this study is the geometry of the fraction resulting from this completion, and the direction of propagation was completely unexpected, and as you mentioned, quite controversial, because it will tell us that actually sigma 3 is important, but not as the strength and isotropy strength of the rock is as important as, and might overrun what we think stressful is in this type of operations.
Very good. Now, Alexei Savitsky has a long question, but I think it's kind of a pertinent one, so bear with me. So first of all, he appreciates, a great presentation and awesome results, and then core through observations that have been made, crosswell, fiber optics monitoring, etc., and image logs in the Eagle Ford, the Permian, clearly indicate planar fracture growth at a large scale, and mostly tensile failure at a core scale. And he suggests that these observations are not consistent with the past and with your experimental observations at a small scale. So why do you think the experiments are not capturing these in situ observations? What can we still learn from? He's questioning what we can learn in addition from our laboratory experiments.
Well, I can speculate because I'm not sure what exactly data and the results is referring. But I think our interpretation is that you need to account for the rock and how that rock and the strength of that rock, especially how weak or strong your bedding planes are, is going to influence what is your final result. So in the Eagle Ford, I think the stress regime is completely different, and also the rock, depends where you are, is much more competent and more, I would say, isotropic rock. That is for the little I know of the area. I never worked with samples from Eagle Ford. We would love to, but is so really depends where you are, and you need to know your reservoir, but what we see is that there are also many other published data that will support our interpretation. So, but it really depends on where you are, what is the stress state, and what your rock is. So, what we are saying is not opening bedding planes is universal, but is something that plays a huge and important role in many of the plays around the world, we think, but definitely in the mountains and the Duvernay, I think, in Canada. So the equation.
Very good. Well, you got time for lots of questions, guys. That's the risk of finishing after 35 minutes. Anyways, Shahrazad Rashankar, Shahrazad wants to know if you scanned the experiments, if you scanned your experimental samples before and after the hydraulic fracturing tests, and if you have other diagnostic methods such as AE.
So okay, we're going to take a lot of time here to explain.
Okay.
So the answer is yes. We CT scan all cubes before and after the experiments. So the cube are 8 centimeters. So the diameter is about 14 centimeters. That with this instrument we had, that led us to a resolution about 110, 120 microns of offset size. And that was able to tell us something about anisotropy in the material, but will not tell us very much about the presence of fissures and really small cracks that were there before or being produced during the experiment. That is why we devised a destructive, very tedious methodology that we calls is called serial sectioning of the cube. And if anyone is interested, we published that in Rock Mechanics, Rock Engineering a couple of years ago. So that methodology is based on freezing in place our freezing, injecting epoxy into the hole. Is a fluorescent epoxy that will glue the cube and keep the cube at the state where it was at the end of the experiments. And then what we did was start grinding one face down. So I can search for a little bit more. I have a slide somewhere. In a second. Oops, I stopped shared. I need to look for the slide. In other words, we'll start grinding, slicing our cube in a very tiny ways, and that allowed us to reconstruct the full cube in at a resolution of about 50 microns. So if you can imagine what we were doing, we were it took really a long time, but this basically is the results. So we were able to take more than 1,000 pictures, and from the thousands pictures, we were able to register and then segment our fraction network. That is how we recreated our very high resolution features for such a large block. Now, the system that we have at the University of Toronto is a polyaxial machine that was conceived and built and commissioned by Professor Paul Young. And one of the key and I think unique technical capabilities of such a system is that is equipped with 3 AE sensors in each plate that will allow us to really fully monitor the acoustic emission events during our test experiments. But the rock is super silent. And what happens is that despite we have, at the end, we had 15 active sensors to cover the full rock block, we couldn't really get no more than one single event that when we tried to relocate was sort of in the area of our bi-wing fracture that opened that we call the hydraulic fracture bi-wing, but nothing was coming or was harvested from the bedding planes opening. So those bedding planes were so silent that were not really monitored. And that is what we think is also happening in the field. The microseismics is missing a lot of what is happening. So basically it's not able to monitor the part of the bedding planes. Now, quite a few years ago, I remember that ESG that presented a paper in the Liar Basin, where they will monitor completion of the Liar Basin, and what we saw was really a competition in between a bi-wing vertical classic fracture and opening and parting of bedding planes, and apparently they had the sensors so close to the fracture path that they were able to capture some of these very high frequency, almost silent events that were associated with really particle bedding planes. So despite all what we had in place, we were not able to really get any AE, and only one, despite the fact that the fracture was definitely opening. Many fractures were definitely opening, and the end results of our stimulated rock volume is the reconstruction that you see now.
Well, I'd call that a comprehensive answer to that question.
Thank you.
So Martin has brought up a particularly important point, and bear with me, Martin, if I try and paraphrase this, that in formations similar to what you're talking about and where there is bedding plane slip, one of the consequences is often casing deformation. And people are often looking for mitigation technologies for that, and sometimes that includes pumping a spearhead of viscous fluid to initiate a fracture in a particular way. And he's wondering if you have conceived or carried out any experiments where you might have started a fracture with a viscous fluid and followed with slick water.
Well, thanks for the question. And that allows me to advertise for the next phase of our consortium. And we are looking at sponsors that will allow us to carry out such a type of experiments. We have quite a list of options that we would like to try, and we're looking for enlightened companies that would be willing to invest in us for the next 3 to 5 years to carry out this type of experiments. This allows also me to sort of advertise two things. One thing is that right now we're going to have 3 different polyaxial system. The one that we talked about today that will accommodate an 8 centimeters cube, so about 3 inches cube shy. We have a 1 foot vessel that will accommodate a 1 foot, so basically a 30 centimeters cube. And we have our megalith, very low stress that can be completed as well. And all of those, and the 2 larger vessels, we plan to run viscous slick water completion. We can run multi-well, multi-stage, and that is the plan. And that is what we are looking for additional sponsor to support this type of research. Thanks for the question and the opportunity.
So Pat McClellan is wondering if you've had the opportunity to compare your data with actual DFIT data that's done in the Montney Formation, you know, some distance away from Canmore.
That would be
yeah, no, I need to delete that, not delete, to defer that question to the conference in October, because that is part of what we are currently doing, and we are planning to discuss that at that particular conference. What I want to say, and sort of spoil a little bit who is going to be there, the data we have access to from the Montney completions, they seems to fit very well in place with what our observations are within the cube and with the model that I presented here that was done by her. So I think that we'll discuss this more in Banff in a month. So I prefer not to say that.
Very good. So come and listen.
Pretty much, yes.
Yes. Okay. And actually, Igor Dontsov and Igor has a comment, and I might just let Igor unmute and indicate his perception of which domain these fractures are in.
Sure. Thanks, John. So I mean, it just basically comment in relation to the S question about the fracture regime and Alexis question. So the idea is that, I mean, if you scale down to the lab, and if you want to preserve your fracture regime, typically you need to increase viscosity by a lot, right? By 2-3 orders of magnitude compared to the field, just because your fracture scale is much smaller. And since you use slick water, so what it means that it's very, very likely you're very deep in the toughness dominated regime, which means that all the fracture behavior basically is determined by all these rock heterogeneities. It's determined by more rock than the fluid, right? And so you basically, your fracture feels all these little differences in rock fabric, right? And so that's in turn promotes complexity. And this is not necessarily what we see in the field, because in the field we based on the scaling, so we have more effective viscosity. Okay, and so and the second comment related to this is that on a lab scale like this, typically the fracture pressures, the net pressures are much higher, again, just because the scale is much lower. And so even though you have the same stress anisotropy as in the field, right, so your fracture pressure is much higher, and so it can exceed sigma H max, for instance, right, or even sigma V. And so this in turn can open fracs in other directions, and which this is not necessarily happening in the field, right? So this is just another factor that contributes to complexity that we see in the lab, which we not necessarily may see in the field. Okay, but I mean, we don't know exactly what's happening in the field, but again, there's some indirect evidence, as Alexei mentioned.
Sorry, can I ask you to actually? I'm asking you a question now. Why do you say that there's a higher pressure in the lab with respect to the field?
Well, I mean, in all the at least from the modeling side, right? So your fracture net pressure, I think is roughly inversely proportional to fracture size, and so your fracture size is much smaller, and so this makes your net pressure much higher.
But you assume that your fluid flow injection rate is the same, right?
No. Well, I mean, we can actually do the math. I mean, if you want, we can talk afterwards. I mean, we can do the math. I mean, just for a simple radial fracture, we can put all the numbers in and see what the values of the fluid pressures are, and do the same numbers for the field and see the difference.
Because what we did, and that is actually was not said, the way we try to scale all the tests from field operation to the lab, to the small cubes, we played on the injection rate, and what we did, we calculated the pressure that the fluid injection would create on our open well, and scale that to so basically the pressure rate that the rock would see in the lab is exactly the same pressure rate that the rock would see in the well. That is why we scale the two experiments.
Okay.
So yeah, we've got 1 minute left. So last question, or last observation, and it's from, well, whoever CCLS 96381 is. Anyways, good question. Thanks for the presentation. One of the drawbacks of generating these horizontal fractures is poor well productivity. And maybe you can't answer this from what you alluded to earlier. Is this consistent with what is seen in production performance in the Montney? And maybe just generically answer that question rather than specific operator information.
Absolutely. So I'm not going to talk about any operators or any results. I would actually flip why it needs to be poor performance. My point is, or what I would say is that, well, if the rock breaks in that, you know where it's going to fail. It's going to fail in very many locations parallel, so you can actually engineer and geosteer your well to take advantage of that, and what you think is going to be a poor well is going to be your best well. And I can tell you that from, and I'm not saying who and where, several operators are actually actively doing that, and they're so happy. But I'm not going to tell anyone, and I'm not talking about the mountain.
Okay, well, on that upbeat note, I'd like to really thank our speakers. Really a very, very interesting presentation, and gets us all thinking about how we can do things differently and understand things differently. So Giovanni and Ali, thank you both.
Thank you very much. And I would like to say that it was a great opportunity, John, for presenting our work. And if anyone has any question, they can reach us at any time by email, and we'll try to answer in not too long.
Okay, very good.
Thank you.
Thank you, everyone.
Thank you.
Bye.